So, hello everyone. So, as previously mentioned, I'm a research engineer at Lagrange, and today I will be presenting you as a method that has been developed by our math research team. So, these authors regarding how to mix and match operators that want to sell their computational power to execute and to prove ZK proof on the one hand, and then on the other hand, we have clients that want to have proof generated and who are ready to pay for that. So, yeah, this is a global setup. We have these people here who want their proof to be run. So they are sending proof to our gateway, and then they are bidding. They are saying that they are ready to pay up to a given amount to have this proof executed and sent back to them. On the other hand, we have operators that are running heterogeneous hardware, more or less powerful, more or less memory, CPU, GPU, and so on and so on. And they are selling their available computational power up to a given amount starting from a given amount of money, and they want to receive proof, run this proof, sending back to the client. And we are in the middle, and we have to mix and match this whole herd of people, and we have to do it in a way that is profitable for everyone involved. So, typically, from an academic perspective, when you are running an auction, you want to satisfy these 5 criteria that are determined to be interesting so that the auction is fair and positive for everyone involved. So you have the truthfulness. So the truthfulness criterion says that the best strategy for everyone involved is to actually bid the money that is really the actual amount. So there is no interest for the seller to underpay, and there is no interest for the buyer to overpay. Then we have the the weak group strategy proofness. So it means that if there is a clique of people who are conspiring either to prop up or to lower the prices, then there is at least one person in that clique for who the best move is actually to leave the clique and not to participate into the collusion. And if you recurse, then there is no interest of being in a collusion with other people at all. You have the welfare maximization. This one is saying that basically we want to extract as much value for everyone involved. So we want the sellers to get as much money as they can. We want the seller to pay as low as possible, and we want the operator to make some margin benefit on the auction. You have the computational efficiency, which means that your algorithm that will be doing the mix and match must actually run in a decent amount of time. You don't want to spend astronomical amount of computation so that it would take 1 week to find the best solution. And finally, you have the weak budget balanced criterion, saying that the auctioneer does not lose money. And given that we are the auctioneer, we don't want to lose money for obvious reasons. So let us now take a little look at what the problem looks like from a graphical perspective, I would say. I would like to present you a very famous mathematical problem, which is the knapsack problem. The knapsack problem is that you have a container, you have multiple items, all of the items are not fitting in the container all at once, and you want to find the best combination of items that maximize the value that you can put in your knapsack, even if you cannot put all of the items. This is a NP complete problem, which means that you cannot find the perfect solution in the general case in a, let's say, a satisfying amount of time. I'm not going to dive deeper into the detail because that's not very interesting for now. But the idea is that finding the perfect solution is not practically possible in all of the cases. So you are reduced to finding heuristic. And if you take a look at our problem, which is this one, it's kind of an extension of the knapsack problem, where each prover would be an independent knapsack, and each proof is actually an item that you want to put in these bags. So there are additional constraints, of course, because we want to mix and match proof and operators, proof and prover, where they have actually compatible prices. So the guy with the proof is ready to pay more than the prover is asking for, otherwise that wouldn't work. We have multiple bags instead of a single one, and so on and so on. But basically, those are very close problems on ours and extension. So we know that we won't be able to find the perfect solution all of the time. So that brings us to we go from the pentafecta to the tetra-and-a-half-fecta of a good auction. We are basically changing slightly the welfare maximization criterion, where we are now going to not maximizing the value generation of the auction, because that wouldn't be possible in a finite amount of time, but, well, at least in a decent amount of time, but we are going to just ensure that the value that we generate is actually positive and that everyone is making money. So not the best solution, but a good enough solution. So what is the strategy that our research team designed? It's first to define a family of algorithms, then prove that this family of algorithms is actually satisfying these 4.5 criterions that were defined. Then you find a family of parameters for these algorithms that are giving you instances of the algorithms that are compatible with the problem at hand. And finally, you apply it. So what are the parameters, so the moving parts of this family of algorithms? So we need 4 of them. First, you have a ranking for the clients and the provers, and you want a ranking function that will be taking the list of clients and their bids, the list of provers and their provers, and rank them in a given order. There are a lot of criterions for this ranking that you can find in the paper, but I'm not going to delve into the details too much here. Then you must have an asymmetric composition rule. So this is a function that is taking a match between a prover and a proof and saying whether the match is acceptable or not. You have a third function, which is the asymmetric composition. The asymmetric composition is taking basically the ranking of the prover, ranking of the clients, the composition rule, and creating a match between the clients and the provers. And finally, you have a payment rule that will be taking the result of this function and defining who will be paying how much to whom. So if we take an example of the algorithm, we could take, for instance, a ranking for the clients where we rank the proof by the value offered divided by the required computational power. So you have some kind of price per ratio. For the prover, you can say that you are going to rank them by a decreasing amount of price, basically. So the prover asking the lesser money are first, and then the prover asking for more money are at the end. And then you are going to fill the one into the others until you reach either a place where you don't have enough computational power to fill that into that, because this one is too big for this one. And then to satisfy the rule about the non-collusion, you are going to kill the latest match that could have fit, but we are still going to kill it for mathematical reasons. I'm not going to detail. But this is a general family of algorithms that is defined. So now, how does that work? And how can we go from the theoretical paper to something that is actually working in the real life? So, of course, there is a lot of criteria, assumptions that are made on the purely, let's say, ethereal world of mathematics that is not working in real life. So first, we have a temporal dimension, because the paper only describes a single instance of an auction, but we have a continuous process where we will be running for days and days and days and running thousands of proofs on thousands of machines. So of course, you need to discretize this space so that you have multiple successive instances of the auctions, and you have to be to add some details for that. Then you have also, this is real life, so sometimes people have issues. You have provers who break down, you have clients who have some issues, you have network breaking down, and so on and so on. So you have to create some kind of barrier to entry so that the people that are not really able to participate in the auction right now cannot get into the auction. We have some client-specific criterions because some of our customers may have some requirements that they want to apply to the system. And finally, you have to discriminate between heterogeneous hardware, because in the real world, you will have some proofs that will be running on CPUs, some that will be running on GPUs, and so on and so on. So you have multiple classes of provers that can only be matched with certain classes of proof. So that was basically it. This is, as for those of you who were there like 15 minutes ago, this is the heart of the system that our CEO Ismail described, and this is how we are currently working with zk-sync or with Polygon on the proving market. So thank you for your attention.